So there are many reactions that operate via nucleophilic acyl substitution that have specific names, and these are known as named reactions. And the mechanisms are sometimes more complicated than just substitution at the carbonyl carbon, but they have unique characteristics that make you able to convert between functional groups. And so each reaction that we're going to go over now provides unique ways to create sort of rare functional groups. So the first reaction that we're going to come across is known as the Beyer-Villiger reaction. And the Beyer-Villiger reaction takes a ketone, and when you take a ketone in the presence of a per acid, and so the per acid we're going to use here is the trifluoro version. Of course, you could use MCPBA. That also works. In the presence of a per acid, you can take a ketone and make an ester. So how does this work? Well, the first thing that happens is that the lone pairs on the oxygen of the per acid are going to attack the carbonyl carbon. And so when that happens, you're going to get a tetrahedral intermediate. Okay? And so we get this tetrahedral intermediate here, which has positive and negative charge separated. And then, of course, we can get a proton transfer event happening to give us a neutral species. Okay, at this point is where we make the key bond forming event. And so the next step of the reaction is that the lone pairs move down to form a double bond. But then what happens is the carbon bond between the formerly carbonyl carbon and the R prime group attacks the sigma star oxygen-oxygen bond. And that breaks the oxygen-oxygen bond. And so what you're left with is a species that has a proton still attached to the carbonyl and oxygen in between the carbonyl carbon and the R prime group. Of course, you have trifluoroacetate as well, and trifluoroacetate is then going to deprotonate the protonated ester to give you the final product. Okay. Now it's at the stage of the rearrangement where we have some important things going on. And so there's something known as the migratory aptitude. So let's say we have R and R prime that are different. How do we know which one is going to be the one that moves? And so the migratory aptitude is the potential for something to migrate. And so hydrogen atoms are, of course, going to migrate first. Then you have tertiary alkyl groups, so something like a terbutyl group. And then you have secondary alkyl groups. And then you have aryl groups after that. Then you have primary alkyl. And then you have methyl. And so the hydrogen moves the most, followed by tertiary alkyl. And so this trend allows you to think about how you're going to make which specific ester. Okay, let's move on to a different reaction. This reaction is known as a courteous rearrangement. Okay, in a courteous rearrangement, we start with an acid chloride. And we're going to take an acid chloride and react it with sodium azide. And over the course of this reaction, what we're going to generate is an acyl azide. Okay, and so the first thing that happens is that we get sodium azide is going to be nucleophilic at the nitrogen, is going to attack the carbonyl carbon to generate a tetrahedral intermediate, and that tetrahedral intermediate is going to collapse with loss of the leaving group. This time the leaving group is chloride, and you get the acyl azide. The courteous rearrangement part of this mechanism is the next step. So the next step is you take an alcohol in the presence of heat, and when you heat it up, what you get is a functional group known as a carbamate. Okay, a functional group known as a carbamate. Okay, so how does this exactly work? Well, the acyl azide, we can sort of draw out the Lewis structure of the acyl azide. Lewis structure of azide looks like this. So we've got positive charge here and negative charge here. What happens in this reaction is as you heat it up, you're going to undergo a rearrangement. And so we have to follow along the set of arrows here. And so the lone pairs on nitrogen move down to form a double bond. The R group is going to move over and populate that sigma star nitrogen-nitrogen bond, which then breaks the nitrogen-nitrogen bond. So you're going to release nitrogen gas as a byproduct of this reaction. And if you follow along this set of arrows, what you get here is a new functional group that we haven't talked about before, we haven't come across. This is known as an isocyanate. Isocyanate is then going to get trapped by the alcohol. Right, so nucleophilic attack of the alcohol, right, onto the carbonyl carbon. Right, electrons move up onto nitrogen as a lone pair, and then you get the following. Okay, so we have R prime with a positive charge, and then we can of course get a proton transfer event happening to give us the neutral carbamate. Now, one more thing about this reaction, if the R prime, the alcohol, is equal to a hydrogen, right, which would mean that you have water in your reaction instead of an alcohol, what we say the product will decarboxylate. Okay, and so at the end of the reaction, you're going to have something that looks like this. This is going to decarboxylate. So what you're going to get is an amine plus CO2 gas. And of course, this is a good way of making an amine in this reaction, right? So you can, of course, generate the carbamate over the course of this reaction if you use an alcohol. But if you use water, the product will decarboxylate, and you will get an amine as your final product. All right, let's talk about a similar reaction to the courteous rearrangement, and known as the Hoffman rearrangement. Okay, so the Hoffman rearrangement starts with a primary amide, and we treat the primary amide with sodium hydroxide and bromine, molecular bromine. And the product we get, just like in the courteous rearrangement with water, is an amine. Okay, so how do we do this? Well, the first thing that happens here is we get a deprotonation with sodium hydroxide. Okay, so we get nitrogen with a negative charge on it. That nitrogen is then going to react with bromine. All right, and so we're going to brominate the nitrogen. We simply attack the sigma star bromine-bromine bond, and then we're going to get that N-bromo species. Now, hydroxide can come in again, and it can do another deprotonation. And so this time we're going to get a species that looks like this. And then once again we can get a rearrangement to happen. And so the lone pairs on nitrogen are going to come down, form a new carbon-nitrogen double bond. The R group is going to migrate over, populate that sigma star nitrogen-bromine orbital, which displaces the bromide. And so you're going to get another isocyanate, plus this time bromide anion. Now it's at this point where you still have hydroxide in your reaction mixture, so hydroxide can come along and it can attack the carbonyl carbon. Okay, so we have this type of species. This can undergo a deprotonation, right? And that's going to give you the NH C double bond OH. Okay, this is going to decarboxylate. A simple decarboxylation like this is going to give us CO2 gas plus the amine that is deprotonated. And so all we have to do here is work up this reaction with a proton source, something like strong acid, a strong HCl, sulfuric acid, something like that, and we get the free amine again. Right, so Hoffman rearrangement, courteous rearrangement, they can, if you're using the appropriate nucleophile, give you free amines as your product structures. Let's do another reaction that's actually really similar to this, and that's the Wolff rearrangement. So this is number 4. Okay, the Wolff rearrangement. So the Wolff rearrangement starts from an acid chloride, but uses diazomethane as the nucleophile. And so if you recall, diazomethane has the following structure. And what we can do is we can form the ketone here, and if you were to heat that up, what you would get is a functional group known as a ketene. Okay, so how does this work? Well, the first thing that's going to happen is a nucleophilic acyl substitution mechanism. Right, so remember, these are named reactions in nucleophilic acyl substitution, so there must be some sort of nucleophilic acyl substitution mechanism in these reactions. So we get nucleophilic attack of the carbon of diazomethane onto the acid chloride, and that's going to give us this tetrahedral intermediate. Okay, we get collapse of that tetrahedral intermediate with loss of chloride as a leaving group. And we have a positively charged intermediate, which under these conditions with chloride hanging around, we can get deprotonation of one of those two protons to give us the neutral species. Okay, it's a sort of a zwitterionic species, positive and negative charge. Okay, so at this stage, what we can also get, and I'll just redraw it over here because I need to give myself some space, is we can get the rearrangement to happen. And so the rearrangement is sort of the same set of arrows that we sort of had before. The Lone pairs, this time on carbon, are going to move in, form a double bond. This R group is going to populate the sigma star carbon-nitrogen bond, and you're going to release nitrogen gas as a byproduct. And in the process, you're going to generate this new functional group known as the ketene, in which this is an sp hybridized carbon. Now, perhaps I can draw this a little bit differently. I can say that the lone pairs are up here. Lone pairs move in, form a double bond. This bond breaks, forms a new carbon-carbon bond, and then releases nitrogen gas. And so you form a ketene in this reaction. Okay, let's extend this type of reactivity one more step. So we're going to do something known as an Aren Ice Dirt reaction. So the fifth reaction is known as the Aren Ice Dirt. And really takes advantage of this ketene intermediate. So let's follow along here in a synthesis. So if we take some R group, carboxylic acid, we make the acid chloride by treating it with thionyl chloride, and then we react it with diazomethane. We can get the ketone, this acyl diazomethane, and if we heat it up, we can of course form the ketene. Now if we then treat the ketene with water, we can generate what's known as the homologated carboxylic acid. And so homologated carboxylic acid, if you look at the original starting carboxylic acid and the product carboxylic acid, you now have a CH2 embedded in between the R group and the carbonyl carbon. Right, so it's like you're extending the chain in between the R group and the carbonyl carbon by one carbon. Right, so how does this exactly work? It's really similar to the way we had an alcohol attacking the isocyanate or water attacking the isocyanate. Because what's going to occur here is you're going to get water to attack your ketene. And as water attacks the ketene, it traps that ketene. You're going to get an intermediate that looks like this. This is then going to undergo a deprotonation to give us a neutral species. And this is going to tautomerize to give us ultimately the carboxylic acid, homologated carboxylic acid product. So a homologated carboxylic acid is just one in which you have an extended chain length. Right, so this is really an application of the Wolff rearrangement. You're doing the Wolff rearrangement followed by trapping with water. That's the Aren Ice Dirt reaction. Okay, so switching categories a little bit, we want to talk about the next reaction, which is known as the Beckman rearrangement. Okay, so the Beckman rearrangement starts with a ketone, and And we're going to react this ketone with hydroxylamine in dilute HCl, or dilute proton source. And we all know that you can get the oxime in this case. But in the presence of this proton source and heat, you can actually rearrange this product to give you an amide. Okay, so let's figure out how this might occur. So let's actually start from the oxime itself. So the oxime itself is going to first protonate. Right, so we have this positively charged species. You can see that the sigma star nitrogen-oxygen orbital is directly aligned with the carbon R group bond. And so what can happen here is you can get a migration of the carbon-nitrogen bond into that sigma star nitrogen-oxygen orbital, displace water at the same time that the nitrogen lone pairs are moving down. Right, so what you're going to generate here is an R carbon triple bonded to nitrogen, singly bonded to an R group. Now at this point, this intermediate is very electrophilic, and so water, which was liberated in this reaction, can of course come back, attack that carbonyl-like carbon, and it's going to generate an intermediate that looks like this. We can, of course, become a neutral species. And this neutral species can just tautomerize to form your amide product. Okay. And so we have a good way of taking ketones and making amides out of them. So very similar to the way that we took ketones and made esters out of them. Similar type of rearrangement mechanism. All right, let's do next reaction known as the Rosin reaction. Okay, so the Rosin reaction takes an acid chloride and generates an aldehyde out of an acid chloride. And the reagents for this are hydrogen and palladium on carbon, hydrogen and palladium, excuse me, quinoline, and barium sulfate. Okay, so very similar to the Lindlar's catalyst, except you don't have any lead tetraacetate. And so it's hydrogen and palladium on barium sulfate with quinoline gives you the aldehyde. And we won't really go through the mechanism of this reaction, but what I do want to talk about is a reaction that is similar to the Rosin because you can think of the Rosin reaction as being a reaction that has a hard nucleophile involved. You can take an acid chloride in the presence of what's known as a cuprate. And in the presence of a cuprate, you can generate the ketone. Right, so the Rosin reaction generates the aldehyde, but cuprates generate ketones. And normally we would, if we were to take, let's say, an organolithium reagent or a Grignard reagent with an acid chloride, we would add twice because it's a hard nucleophile, and you would generate the tertiary alcohol. Well, this doesn't happen here. And the reason this doesn't happen here is because cuprates are soft. And because they're soft, they're only going to add in once. And so what does a cuprate look like? Well, a cuprate looks like this. We've got a negative charge on copper, positive charge on lithium, and so you're going to add in to your carbonyl carbon a single time to generate a tetrahedral intermediate, and then that's it, right? Upon workup, you get collapse with loss of the leaving group to give you the ketone. And so the cuprate is a little bit less reactive than a organolithium or a Grignard reagent, so it's more selective. Less reactive, and it's more selective. This is an example of a cuprate reaction. Okay, so we talked about, let's say going back a little bit, we talked about ketenes. There are a couple of other reactions of ketenes that we might want to add into our list. And so let's say we've got some ketene. It doesn't matter what the substitution is. If we react a ketene, of course, with an alcohol in the presence of catalytic amount of acid, we can generate this ester. We can, of course, react that with a thiol, and you're going to generate the thioester. And, of course, you can react it with an amine as well. And let's say this is happens to be a secondary amine. You can create the secondary amide in this case. Okay, so same mechanisms here involving nucleophilic attack onto that ketenyl carbon, followed by some deprotonations and some tautomerizations, very similarly to the Aren Ice Dirt reaction. Okay, so we've got two more reactions here. The next reaction is known as the Hansecker reaction. And the Hansecker reaction takes a silver carboxylate. Right, so we have a silver salt of a carboxylic acid. And you have to start with the carboxylic acid. So what you normally do here is you normally take a carboxylic acid and you treat it with silver oxide, and that is going to generate your silver carboxylate plus water. And it's this silver carboxylate which is going to be your starting material in this reaction. And so what is the reaction? The Hansecker reaction takes a silver carboxylate in the presence of bromine to generate alkyl bromides. Okay, so how does this work? What's first going to happen is you're going to take the silver carboxylate and react it with bromine. So your oxygen lone pairs are going to populate the sigma star bromine bond, generating a new oxygen bromine bond plus bromide anion. Now at this stage of the reaction, what's going to happen is the oxygen bromine bond is fairly labile homolytically. And so you will generate two radicals. Your first radical is going to be your carboxy radical. Your second radical is going to be your bromide radical. Now the bromide radical is going to be in very small amounts, and the carboxy radical, also in small amounts, can undergo a decarboxylation. And so we can generate here CO2 gas plus an R dot, so a radical that is on carbon-based radical. Okay, at this stage, the R group is then going to react with another molecule of your brominated carboxylate. And so you're going to get a bromination event happening to generate your R-bromine bond plus the carboxylate again. And the carboxylate can then go back to the beginning and brominate once more, and it, of course, recycles. So this is another type of radical mechanism that generates now a new way of making alkyl bromides. Okay. All right, so the last reaction in this section is decarboxylation reactions. So the decarboxylation of carboxylic acids. Okay, so when we have something known as a beta-keto acid, so this is a beta-keto acid. Why is it a beta-keto acid? Because if we're starting here, this is the alpha position and that's the beta position, there's a ketone at the beta position. Beta-keto acids will undergo decarboxylation. And so I'm going to redraw this slightly suggestively. So I'm going to basically rotate around this carbon bond here. And when I do that, that's going to place the hydrogen atom of that carboxy group right in line with the carbonyl carbon. And so what can happen here is that in the presence of heat, you can get a decarboxylation to occur to give you the ketone plus CO2. And so what does occur is you get a sort of an aromatic-like flow of electrons. You can get a flow of electrons that looks like this, in which the oxygen-hydrogen bond forms a CO2 molecule. The carbon-carbon bond moves over to form an enol, and the carbon, of course, carbon-oxygen bond grabs the hydrogen to give you this enol. And this enol we know is going to tautomerize to give you the keto form. Okay. Now in this particular reaction, the R group, so the R can be an alkyl or an aryl group. Right, but it can also, it can be OH or OR. And so if the R group was an OH group, you would get a carboxylic acid as your product. If it's an R group, you'd get OR group, you would get an ester as your product. So it depends on your functional group. Now, what happens if you have the following species? Let's say you had some X group here, and you've got a carboxylic acid like that. We say that these groups are unstable. Right? So X here is equal to an oxygen or some N R group. As we said before with the courteous rearrangement and the Hoffman rearrangement, these things will decarboxylate. Okay, and so we get CO2 to form. Right, again, where X is equal to oxygen or NR. Right, so you have to be careful with carboxylates and their decarboxylation capabilities. When you have beta keto acids, those will decarboxylate. But when you also have these unstable species in which you've got some heteroatom directly attached to a carboxylic acid, those will also release CO2 to give you, in this case, the free alcohol or the free amines. And we've seen this already here with the Hoffman rearrangement and the courteous rearrangements. And so that kind of ends our discussion of nucleophilic acyl substitution. We now have 10 different sort of named reactions that somehow involve this nucleophilic acyl substitution mechanism.